technical difficulties. As I said, network analysis, there's a recent textbook on network analysis by Newman in 2010. Network analysis basically is a mathematics of pairwise relations and the structures that can be built out of pairwise relations. By that I mean things that can be represented in a set of nodes and connections between those nodes, which are often referred to as edges. And this mathematics comes with a whole set of tools for characterizing different kinds of networks. Here, for example, is a picture of a regular network in the top left, and a small world network on the top right, and a random network in the bottom section here. And one set of vocabulary that network analysis supplies is a way of categorizing different kinds of networks. It also supplies a set of concepts for talking about the structure of networks. And this is very important because when we're dealing with very complex systems that have many, many parts and many, many interactions with one another, it's very useful to have a set of tools for representing that complexity in all of its detail. And I'll introduce some of these concepts in just a second. Concepts like path length and modularity and clustering are really central to the work that I'll be talking about today. And this mathematics also comes with a set of algorithms that will allow one to analyze a network. And for instance, to say how the network can be broken into subnetworks, and that those subnetworks can themselves be broken into subnetworks. And I'll talk a bit about those as well. And behind all of this is a mathematics for proving formal results about how networks will behave, or properties, which properties follow from having a small world network as opposed to a random network or a regular network. Two fundamental ways of representing networks are depicted in this diagram. Here you see represented most explicitly the nodes and the various edges connecting those different nodes. But this kind of spatial diagram of connectivity among a bunch of nodes in a network can also be represented in the form of a matrix. Each row in this matrix represents an individual node. And each spot, so all of the nodes are represented here and here, and each dot represents a connection between those two nodes in that matrix. So for example, if we focus here on this node, that's a node that has very low degree. That is, it has very few edges with other nodes in the network. And it's represented here in the network, and you can see the two edges that it has with the other components represented there. This is this node here has a high clustering coefficient, and you can see that it's very tightly connected with other nodes in its cluster. And that's represented in the matrix as well. Here's a node that has high centrality. That is, it exists between two clusters of two subnetworks in this network. And you can see that that's represented here, and you can see that in one network it's got some connections, and in the other network it's got some connections as well. And furthermore, yeah, I think that'll be very good. And finally, last but not least, here we have one that has very high degree. That's represented in the matrix here, and you can see that it has more colored in boxes than any other node represented in this matrix. And we can talk about things like the degree of a node. I've mentioned that a couple of times here, how many edges it has. We can talk about a clustering coefficient, how tightly connected the various nodes are to one another. We can recognize in networks various sorts of motifs, like these triangular organizations that one finds, or these V-shaped organizations that one finds. We have constructs like path length and the distance between two nodes. When one is, for instance, interested in the 7 degrees of Kevin Bacon, I don't know if you've ever heard of that, but how many connections through movies you have to go before you can connect any given actor or director to Kevin Bacon, that's a simple matter of path length, right? And then we can also talk about various kinds of community structure. In this case, we've got really 2 modules inside this network. And part of what I'll be talking about today are algorithms that will take very densely connected networks and tell you which nodes in that network belong in the same clusters with one another and which are in different clusters from one another. identifying a community structure inside the network. Now, network analysis, this kind of mathematics, has been applied not just in neuroscience, but all over the sciences. And I think we're going to find that happening increasingly over the next decade or so. So it's been used to describe, obviously, Facebook and friendship connections. It's been used to describe the internet generally and movie databases like, Kevin Bacon. The dolphin communication case is especially interesting for clustering purposes, where they looked at networks of interaction between different dolphins and were able to identify subgroups within a pod of dolphins. And when the key central dolphin died, the two pods went their separate ways, indicating that in fact that node was really central to the network. But it's also used to describe cell networks and food webs, co-citation networks in academia, airports, telecommunication. It's been applied to indie bands, and of course Kevin Bacon. In neuroscience, it's also being applied in many different ways, and at many different levels of organization in the nervous system. This diagram, which comes from Patricia Churchland and Terry Sanowski, I think it's Patricia Churchland originally, but also with Terry Sanowski, a representation of different levels of organization in the nervous system, from the entire central nervous system as a whole, all the way down to molecules at the size scale of angstrom units. And up here above the central nervous system, we could have social networks and use network analysis to describe those. It's also being used to describe large-scale cortical systems. And the last half of my talk will be entirely dedicated to that application of network analysis. But you might also have heard about the cellular level connectome, which is a big project in contemporary neuroscience. Projects such as the European Brain, the European Brain Initiative, which are driven by the goal of describing every cell in the human brain and its connection to every other cell in the human brain. Sub-projects of that include Sebastian Sung's work on the connectome in the mouse retina, where he's crowdsourcing the work to map out every cell in the mouse retina and its connection to every other. That's a project that's well underway. And also in genetics, you find people talking about regulatory networks of genes. Really today I'll be focusing on mostly on this large-scale brain systems, but I'll also mention a bit about cell-cell connections right now. So as I said, some people are interested in characterizing the connection of every cell in a system to every other cell in a system. And perhaps the earliest example of this was when people started working on C. elegans, and they were able to characterize all of the cells in C. elegans and characterize exactly how each of those cells connects or does not connect to every other cell. And as I pointed out, Sebastian Sung, who wrote this book, I Am My Connectome, is in the business of trying to map the mouse retina, and he has the view that we individually each just are a network of neurons, and that our distinct individuality is encoded like a fingerprint in the distinct connectivity of our brains. That's a bold thesis, and one that perhaps at the end of our talk today we'll have a little more perspective on. Now, a few years ago, Obama decided to fund a major brain research initiative, and it's really at this level of organization that he's primarily interested in, looking at electrophysiological interactions among the cells at that level of organization in the nervous system. But as I'll point out, especially at the end of the talk, this kind of mathematics is also being applied to the data that's obtained in functional magnetic resonance imaging devices of the brain at rest. And the data that is delivered by those devices is then put through various kinds of network analytic tools to reveal things about the gross architecture of systems in the cerebral cortex. In particular, this is an area of neuroscience that at the moment is underdeveloped. We know a lot about individual brain regions, and we know a lot about individual cells, but exactly how large the brain are connected into meaningful circuits and units or systems or networks, that remains underdeveloped. And the hope is to use the data from fMRI, from resting state fMRI it's called, to reveal something about the system level architecture in the brain. Is this going all right? Is this a reasonable pace to be talking? Okay, great. Okay, so here are some questions that I want to address. I'm a philosopher of science. I work on scientific explanation. So a number of questions have arisen in contemporary philosophy of science about this kind of work. And so I want to blend some scientific background with some philosophical orientation to the question. So one question that arises often in philosophy is, are network models explanatory, or do they do something else? A second question, I'll argue that this is a very bad question. Secondly, do network models provide non-mechanistic explanations? That is, now that we have the tools to apply network analysis to the brain, have those tools brought with them a new paradigm for understanding the way that brains work, a new set of tools for explaining the way that brains work? And I'll consider some things that network models help us to do. My argument will be that no, in fact, in most cases, what network analysis provides is a very complex kind of mechanistic analysis. And that network analysis is especially useful for describing abstractly the structure of a system. I will reject the idea that network analysis deals specifically with non-decomposability, and I will reject the idea that network analysis provides a distinctively mathematical kind of explanation. Now, perhaps it provides some other kind of explanation that I won't discuss, and we can talk about that in the question and answer. But for the most part, I think that network analysis is very useful for helping us to understand the causal structure of the brain. And it provides explanatory information to the extent that it does that, and it does not provide explanatory information when it does not do that. That's the point that I wanted to drive home. So what are they good for? I'm a huge admirer of this work. I have tremendous respect for the people who do it. And I think that what's really going on here is that network models, I'll show you an example of a network model that nobody thinks does any explanatory work whatsoever. And then I'll describe how they use it to analyze brain anatomy and how they use it as a tool for discovery, not necessarily for explanation. That's what I think is really exciting in this work, how to discover the organization of complex mechanisms. All right. So, first question, are network models explanatory? I think this is a really bad question. Why do I think it's a bad question? Because network analysis is a content-neutral mathematical tool. It can be applied to any number of things, regardless of whether they have any explanatory value whatsoever. If I trace co-citation networks, I might not be interested in explaining anything at all. I'm just interested in understanding who cites whom and how often. Network theory, and this is a central theme in this talk, network theory is a content-neutral kind of mathematics. It just requires that you have a set of items, that those items can be treated as nodes, and that we can find some way of talking about relationships between those nodes. Those relationships might be of any number of different sorts. So I think the question, are network models explanatory, is a bit like asking, are algebraic models explanatory? Or is first-order predicate calculus explanatory? Or is calculus explanatory? The answer is, it depends on what the calculus is being used to describe. It depends on what the network analysis is being used to describe. It depends on what the nodes are and what the edges are. Now, I think part of the reason why philosophers have thought that perhaps network models have an explanatory function of their own is that, and that it's distinct from mechanistic explanation, is that they embrace what I call a representational view of explanation. That the explanatory value of an explanation derives from the form of the model that's used to represent it. And the different kinds of explanation are sorted by the different kinds of models that are used. In contrast, I have an ontic view of explanation, that the explanatory force of a model lies in what the model represents, that is, in the reference of the model. So the question, do networks explain, is a bad question, because it depends on what the network is being used to describe. And if they describe the right kinds of things, then it does carry explanatory force. If it describes the wrong kind of things, it does not carry explanatory force. And this question cannot be answered simply by reference to the representational format of network analysis. Who would disagree with that? Well, Bill Bechtel. I won't read this quote to you. But Bill Bechtel has emphasized repeatedly that different kinds of explanation are distinguished by their representational format, and that the fundamental focus of a philosophical theory of explanation should be on the form of the representation, not its content. In my view, this gets the norms of explanation exactly wrong, and I'll explain why in just a second. So, to me, the more fundamental question is, do network models provide non-mechanistic explanations? I think there's a mistaken assumption here, as I've just indicated, and the mistaken assumption is that kinds of scientific explanations are distinguished from one another by the representational format of the explanatory text. So, often people will ask, are dynamical models are they mechanistic explanations? Or are geometrical models explanatory in a way that's distinct from mechanistic explanation? Or are there algebraic explanations? And as I just said a second ago, I think these are bad questions. It depends on what the models are being used to describe. Kinds of scientific explanation are distinguished by the appropriate reference of the explanatory text, not the format of the text itself. In other words, I think there's a kind of category mistake involved in much of contemporary philosophical work on the nature of scientific explanation, which I illustrate here with the help of the Ramones. At the top, you find a cassette tape of the Ramones' live performance at CBGB in 1974. And here we find a CD representation of the Ramones' performance at CBGB in 1974. This, for me, is not a musical revolution. This is a revolution in the format in which we store the music, but not a revolution in the music itself. Right? On the other hand, this is ABBA, and this is the Ramones. And if anything constitutes a revolution in music, this certainly does. And for me, the issue is not how we represent it, but what we are representing. The revolution is here. The revolution is not there. All right. Another thing that's helpful for those of you who've read some of my work on mechanistic explanation, Eric Hochstein, a postdoc that's visiting with us at the moment, has a useful distinction between mechanistic models and models of mechanisms. This will get less abstract here soon and more scientific, but right now I just want to set the stage with this philosophical backdrop. Mechanistic models are models that explicitly represent the entities, the activities, and the organizational features of a mechanism. So here, for example, there are two different models of NMDA-dependent long-term potentiation. I guess this is a model of long-term depression in cells. And we represent the entities quite explicitly, and we use arrows to represent their causal interactions with one another, and we show how they all interact with one another. That is, we model the mechanism by explicitly representing its parts and explicitly representing their interactions with one another. That's a mechanistic model in the sense that it models something as a mechanism. But not all models of a mechanism are mechanistic models. That is, we can convey information about how a mechanism works without drawing a diagram that represents the parts and their interactions explicitly. So in a dynamical model, for example, where we use differential equations or difference equations to characterize the behavior of a mechanism, that model might not represent the parts and their interactions explicitly, but nonetheless represent something important about the temporal dynamics of the interaction among the component parts. A model of a mechanism is much more general. It's a model that has explanatory force in virtue of representing some aspect of a mechanism, its organization or its working. Right? So again, I want to emphasize the ontic side of things. It's about the reference, not about the representation. So for me, a better question is, do network models allow us to represent non-mechanistic yet explanatory relations? That's really the good question here. And I don't want to, by the way, I don't want to rule out the possibility that these new representational tools allow us to see things in the world that we couldn't see before, and that what they allow us to see is genuinely explanatory in a non-mechanistic way, however one understands that sentence. And I don't want to beg any questions against it. So here are a couple of ideas about how we could get network models of the mechanism. This is the C. elegans map that I showed you earlier, that has every cell and all of their synapses with one another represented by edges. This is a map of the structural connectivity of C. elegans. It tells you the structure, how the parts are laid out and how they're connected with one another through physical synapses. The nodes in these cases are cells, and the edges are the synapses. There's another term that people use the term structural connectivity to refer to this kind of map. And clearly, if we understand the structures involved in C. elegans, that's a very important component of a mechanistic explanation. Because any mechanism that's going on in the central nervous system of C. elegans has to work through these connections. It places important spatial constraints on the operation of any mechanism. There's also a notion of effective connectivity. And that's really causal organization, how the parts causally interact with one another. And it's a reasonable assumption that many of the causal interactions in the central nervous system flow down these paths of synaptic connectivity. But there might also be other kinds of causal organization that are not represented here, and nothing in this map tells us whether any of these edges are in fact operative, whether they're working. A synapse could be quiescent, but nonetheless still structurally connected to another cell. It could lack receptors, for example. And then the third kind of connectivity that I'll talk about today is what's called functional connectivity, which is perhaps the worst term for something that I've heard recently. Functional connectivity, in that case, the nodes in the network are going to be magnitudes, and the edges are going to be correlations between the magnitudes. That's it. So the word functional here should not imply to you that those connections do anything, or that they are structural connections in any sense. We're merely tracking correlations, and the width of an edge will be the strength of the correlation. That's it. That's what a functional connectivity network depicts. If one reads functional connectivity as effective connectivity, one is importing causal information into a network that does not contain that causal information. That's why it's crucial to keep these things distinct from one another. Right, why have philosophers thought that network analysis is an important non-mechanistic kind of explanation? Bechtel and Levy argue that network motifs provide abstract explanations, whereas mechanisms are always concrete. That seems to me to be a false contrast. For those of you who saw the talk yesterday, it is perfectly permissible for a mechanist to believe that there are abstract structures in a mechanism that are causally relevant to its behavior. Now, I'll give you an example in just a second. This is a mechanism schema. This is what Yuri Alon calls a type 1 coherent feed-forward network. X causes Y causes Z, and X causes Z directly. And you can find many mechanisms in the world that have that kind of structure. And there are things that follow about mechanisms that have that kind of structure from their having this kind of structure. And you could change things about the parts and maybe change some things about some of these interactions, but so long as this structure remains in place, the mechanism will still exhibit those properties. The relevant feature of the mechanism is not in the details, but in its abstract organization. Let me give you a concrete example. This is the concrete example. And this comes from the work of Astrid Prince and Eve Marder, who studied the stomatogastric ganglion of the lobster, the mechanism that's responsible for opening and closing the pyloric valve and regulating the pyloric rhythm in the lobster for digestion. And what they found, none of these, I won't talk about this data in particular. So here's a lobster, this is the stomatogastric ganglion. What they found in simulations and in actual electrophysiological work was that there are something like 500,000 ways of connecting the cells in the stomatogastric ganglion of the lobster that will produce the rhythm that's required for the pyloric valve to open and close and for the digestive process to continue as it should. 500,000 different ways of connecting the cells. None of those particular patterns of connectivity are required for the stomatogastric ganglion to regulate the pyloric rhythm in the lobster. What matters is a general pattern in the organization of these things. So, as I said a long time ago, if one were to focus on a particular organizational structure, one would miss a pattern in the causal structure of the digestive system that is independent of those patterns among the network realizers. That is, a world viewed only at the fundamental level, just looking at the neurons themselves and their particular connections with one another in all of their detail, would be missing important patterns in the causal structure of the world. And network analysis is a very important tool for getting at that causal structure. Now, part of the reason why this has become a debate is that people associate the idea of mechanistic explanation with maximally detailed explanations. But that's not an association that one should have. Maybe the word mechanism just associates that thought in people's mind. So, for example, Woodward says that it's the generic features of network topology and not the details of those mechanistic relationships that drive the explanations provided. But that's just the point that I've been making all along. Mechanists have to achieve a kind of balance between the drive for more and more detail and the appropriate degree of abstraction that's required to pick out just the explanatorily relevant factors. And for me, the test of that is whether you can change the factors and whether that makes a difference to the thing that you're trying to explain, the explanandum phenomenon. And as Eve Marder's work shows in this diagram, what Eve Marder's work shows is that you can change the particular network connectivity, but so long as you maintain the overall pattern of organization in the stomatogastric ganglion of the lobster, the pyloric rhythm will continue unabated. A second reason why people have thought that network analysis is non-mechanistic is because they say it deals with non-decomposable systems. Mechanisms always involve decomposing something into its component parts and tracing how those component parts interact with one another. And part of what's really quite exciting about network analysis is that it allows us to deal with immensely complex networks with hundreds of thousands of connections between hundreds and thousands of tens of thousands of nodes. Charles Rathkopf, in a really lovely article in 2014, says that what's interesting about network analysis is that rather than using idealization techniques to strip those properties away, all of that complexity, as is standard practice in other areas of science, network science brings them to the fore and uses them to furnish new forms of explanation. In other words, he thinks that what's really distinctive here, contrary to what Bechtel and Levy said, is that network analysis gets you into the details and brings those details very much to the fore. And I think there's something very right about that. His second claim is that, and he says it's his second central claim in this article, is that network representations are particularly helpful in explaining the properties of non-decomposable systems where part-whole decomposition is not possible. Network science provides an alternative method of explaining system behavior. So in the first case, he claims that it deals with all of the details and takes them all seriously, and secondly, that it's non-decompositional. And what I'll say about this first thing is that there's something absolutely right about it and something wrong. I don't think that it's not abstract. And secondly, that there's something confused about this idea of it being non-decompositional. Let me explain why. First, let me say something about what decomposability is. My thinking about modularity and decomposability really traces back to Herbert Simon's work in the 1960s in a book called The Sciences of the Artificial. And he's trying to say how we decompose things into, how we understand the decomposition of things into their component parts. And so he needs an idea of distinct components and interfaces between those distinct components. And he came up with, I think, an extremely clever way of talking about this. He says that a component, what distinguishes a component from its surround is that it has a set of parts itself that interact more intensely with one another than they do with things in other collections. So a module or a subcomponent in a mechanism would be a set of things that interact very strongly with one another and only weakly with things in other clusters, to use that term. So modularity amounts to a kind of carving of the causal world into clusters that interact, of nodes that interact heavily with one another but only infrequently or weakly or via a few well-defined paths with items in other nodes. Is that clear enough? I think this is a very nice formal definition of modularity and near decomposability. And this really goes back to, as my teacher John Hoagland pointed out, that this is crucial to explaining. He says, finding in something complicated and hard to understand a set of reliable interfaces, dividing it into relatively independent components, is a way of rendering it intelligible. To take the giant mess of complexity and to break it into component parts that are isolated from one another. So the question is, does network analysis decompose things into component parts, or doesn't it? One thing to note about network analysis and the mathematics of it is that in that science, the notion of modularity is not an all or nothing description. It's a matter of degree. It's typically measured as deviation from the expected modularity in a random network, where nodes are just randomly connected with one another. But even a randomly connected network is going to have some clusters within it where things interact more strongly with one another than they do with things outside of that cluster. So even in the most random networks the most random organization of complex systems, one is still going to find decomposable structure for the most part. Random networks tend to have Simon near decomposability simply as a matter of chance. And furthermore, the other thing that's worth noting about this is that any network at base is a set of, if it's a causal network, is going to have nodes and causal interactions between them, which is by itself a notion of decomposability. So the real question, I think, contrary to Rathkopf, is not whether networks deal with non-decomposable systems, but rather how much decomposability we find in the systems that we're dealing with. How much intermediate mechanistic organization we can identify, not whether there's any mechanistic organization simplicity. Okay, the third reason that people have suggested that networks provide a non-mechanistic form of explanation, they say that it provides a distinctively mathematical form of explanation. And here we are dealing with a form of mathematics and the things that follow from that mathematics. So Philippe Huneman in 2011 describes mathematical explanation as a case in which you can derive some features of the system by mathematical necessity from certain mathematical truths about the system. And Mark Lang in 2013, in a really lovely paper on distinctively mathematical explanation, says that what's responsible for the explanatory priority in distinctively mathematical explanation is that what you appeal to in that explanation is modally more necessary than ordinary causal laws. An example that is often used to illustrate this point is the Königsberg Bridge example. Are you familiar? Have you seen this before? This is an old mathematical problem that I think was originally solved by Euler. The mathematical problem is to explain why it's impossible to walk around the city of Königsberg at the time that the question was raised, touching each bridge of Königsberg exactly once. And one way to try to prove that you can't do that would be to just go out and try to walk around Königsberg several different ways on several different days and see whether you can in fact ever put together a path that allows you to cross each bridge exactly once. But the intuition here was that it was impossible, that trying to do that would engage you in a kind of impossibility. And if that's the case, if we want to know, if you go to Königsberg and you take a walk around Königsberg and you can't walk around it hitting all of the bridges exactly once, and you want to know why can't I do this, the answer might be given in two premises, an empirical premise and a mathematical premise. The empirical premise just tells you about the layout of Königsberg. It says that Königsberg bridges form a connected network with 4 nodes, right? And three of the nodes have 3 edges, and one of them has 5. And then there's a mathematical premise that among networks of nodes where they all are connected with some other node in the network, connected networks that's called, among connected networks composed of 4 nodes, only networks containing 0 or 2 nodes with odd degree contain Eulerian paths. And so it follows that there's no Eulerian path, that is, an Eulerian path is just a path that allows you to hit each bridge exactly once. And the conclusion is that there's no Eulerian path around the bridges of Königsberg. And the thought is that this provides a distinctively mathematical explanation for why certain kinds of paths through Königsberg are impossible. Not a mechanistic explanation, but a mathematical explanation. And perhaps when we apply network analysis to the brain or to Facebook or to other systems of this sort, it allows us to talk about a distinctively mathematical kind of explanation that's not about causal structure of the system. Now, for those of you who haven't taken an Intro to Philosophy of Science course, let me just give you this classic example about how we would tell. It'll come back to be relevant in just a second to the Königsberg case. Hempel considered a case, I call it Hempel's curse because it's a problem that I think plagues even contemporary theories of scientific explanation. Hempel argued that it was possible to explain the length of the shadow by appeal to the angle of the elevation of the sun and the height of the flagpole. But then he pointed out that you could similarly derive the height of the flagpole from the angle of the elevation of the sun and the length of the shadow. The derivation, in other words, could go in either direction. But his point was that the explanation, even though the derivation works in both directions, the explanation only seems to work in one of these directions. The shadow does not explain the height of the flagpole. It goes the other way around. And now what I want to suggest is that the Königsberg Bridge case is susceptible of exactly the same sort of counterexample. So suppose that Marta goes to Königsberg, and she walks around and she hits all of the bridges of Königsberg exactly once. Right? Well, we could start with the same empirical premise we had before, that Königsberg's bridges form a connected network with 4 nodes. And we could talk about the number of, just leave it there. And we add the empirical premise that Marta walks an Eulerian path through the town. Then we use the same mathematical premise that we used before, that among connected networks composed of 4 nodes, only networks containing 0 or 2 nodes with odd degree also contain an Eulerian path. And we conclude from that that therefore either 0 or 2 of Königsberg landmasses have an odd number of bridges. But it seems odd to think that the structure or the layout of Königsberg is explained by the fact that Marta walked around town. Rather, it seems that the layout of Königsberg is explained by the decisions of the mayor of Königsberg or the people, the bridge builders of Königsberg, not by Marta's decision to walk around town. So, in this case, the explanation seems to be reversible. And why? Why is that reversible? Well, because the structure of the town places constraints, causal constraints, on the possible paths that Marta can walk, but Marta's walk doesn't place any causal constraints on the structure of the town. That is, ontic considerations seem to enter to sort the direction of the explanation that counts as explanatory from the direction of the derivation that would not count as explanatory by any standard way of thinking about it. Maybe I don't need to mention, the people that I'm arguing with here say that they want to capture, you could just say, well, maybe the explanation does work in both ways in this case. But the people who work on this kind of response to mechanism and causal explanation generally take themselves to want to satisfy scientific judgments about what would and would not explain other things. And I think we can agree, perhaps today, that Marta's walk does not explain the structure of Königsberg. And I think they would want that. This is a general problem for those of you who've read Lang's paper and care about these things. Another example of mathematical explanation that he gives is a case where you've got mother bakes a batch of cookies and she can't divide the cookies evenly between her 2 children. Why can't she divide the cookies evenly between her 2 children? Because she started with an odd number of cookies and you can't break the cookies. And that's, he says, a distinctively mathematical explanation. But now we could reverse it. Imagine that she bakes the cookies and she divides them equally between her 2 kids. We know with mathematical certainty that she started with an even batch of cookies. But we don't think that the explanation for her starting with the even batch of cookies is that she distributed them to the kids. Just like the flagpole and the shadow, it seems that the causal order of things determines a direction of the explanation. I use this in another paper to argue that Lang's model of mathematical explanation is incomplete. Maybe there are mathematical explanations, but in these cases, and the Königsberg bridge case, which is central to what I'm talking about today, it appears that ontic considerations about the structure, the causal structure of the world, are essential to decide when we've got a good explanation and when we've got a bad one. So the moral here is that you can subsume a phenomenon under a general model, a network model, a mathematical model, without explaining it. In other words, not all patterns in the world are explanatory. And furthermore, it appears that in these cases, ontic constraints are really crucial to decide on the direction of the explanation. The cookies are baked by mom and delivered to the children. She produces the distribution for the kids. Königsberg's layout places a structural constraint on all of the possible moves around town. And that's not a mathematical explanation. It certainly has a mathematical component, but it's not exclusively a mathematical explanation. It's a mathematical explanation laid on top of a causal mechanical explanation. Let me give you a real example. Those are all toys. But now I want to look at the real case that I worked on for a semester in this laboratory that I mentioned earlier. And it involves applying functional magnetic resonance imaging to the brain. But unlike the standard cases that most of us are familiar with task-based functional MRI, in which you put a person in the scanner and you have them perform a task, and you have them perform a very complex task, and you measure the blood oxygenation levels in different areas of their brain while they're performing that task. Then you have them perform a simpler task that contains many of the components of the complex task minus a few, and you subtract the two images, and that tells you the areas that are uniquely involved in the complex task rather than the simple task, and we can embed subtractions of this sort all the way down to the point where we simply have the person laying in the scanner and staring straight ahead, perhaps at some crosshairs. And that's usually the bottom level of a subtraction study in task-based fMRI. But what's happened in the last 10 years in neuroscience, maybe even more recently than that, maybe like the last 8 years, is that people started becoming very interested in what the brain is doing in this rest condition. And they've developed a set of tools that they're known as resting state functional connectivity. And here's how resting state connectivity works. You have somebody lay, hopefully motionless in the scanner. If they move, it creates all sorts of artifacts that are really quite problematic. But you have them lay in the scanner motionless, and then you just take a long-term picture of what's going on with the blood oxygenation in their brain during that time. And you do that for each of the 3 millimeter cubes, voxels, in the brain. Then what we're going to do is to take that information and really what we're going to be looking at over long periods of time are fluctuations in that bold signal. I'll show you pictures of it in just a second. Then we're going to filter out all of the fluctuations with periods, all but the signals that have periods between 10 and 100 seconds. Really long time frame fluctuations in the bold signal in each voxel of the brain. Then we're going to determine the correlation coefficient between the time courses of those bold signals of each voxel with each other voxel in the brain. That correlation will then define the edge. They're the edges in the networks. So in this kind of work, rest is the task condition. Rest is the situation that we're primarily interested in. Exactly how this gets done is complicated. But let me just walk you through a relatively simple picture of what I was just trying to say in words. So here's an area of the brain, and suppose that we're measuring the bold signal in that area, the blood oxygenation level dependent signal. It's about the ratio of oxygenated to deoxygenated hemoglobin. And we track how that ratio changes over time. Right? Now we take another area of the brain, this orange area of the brain, and we map its fluctuations, and then we see the correlation between those two fluctuations. And we could do that again for this area of the brain, or this area of the brain, or this area of the brain, or this area of the brain. And in those cases, we get different correlation coefficients for the fluctuations in this bold signal. Right? Now we take all of the voxels in the brain and we put them together in a giant matrix, 10,000 by 10,000 matrix, where each node, each row in the matrix, you get the idea of what's going on. So now we're taking all these brain areas, we're monitoring the fluctuations of the bold signal, the time course of the fluctuations of the bold signals. We're getting correlations between the time courses and the fluctuations of the bold signals. We're doing that for all the voxels in the brain, and then aggregating it into a matrix. And what we get in the end is a Pearson correlation map that relates the bold time course in every node of the brain to the bold time course in every other voxel of the brain, or every other node. This is what I was talking about when I talked about functional connectivity. This is a correlational network. When we say that these things are functionally connected, we clearly do not mean that they are causally connected with one another. We're merely tracking correlations between the bold signals in each of these nodes of the brain. It's a Pearson correlation, the edge, not a causal relationship. Now, how do you choose the nodes that go into this analysis? Well, what I was describing earlier is this voxel-wise analysis, and you get 10 to 15,000 voxels correlated with 10 to 15,000 voxels, and you get a very complicated matrix of the sort that I walked you through earlier. The other thing that you can do is to start with the meta-analysis of functional magnetic resonance imaging, task-based functional magnetic resonance imaging, and to identify 264 brain regions that we think are likely to be important brain regions. And then we can measure that fluctuation in the bold signal in those brain regions, and we can map 264 nodes to 264 nodes. Working this way is obviously computationally much less demanding than working this way. And my experience working in the lab on a fairly old computer was that I would put data in even for this, and I would type in a line of code that would tell it how to do some manipulation on it. And then I would come back 8 hours later when it was done doing all of the work that it had to do to make this happen. What's really interesting, I think, is that regardless of which method you use to define the nodes of the network, you get roughly the same results. They correspond. These are those 264 brain areas that we're talking about. And that's what a 264 by 264 matrix looks like. Somewhat more complicated than the network that I showed you before. But you can already see, just visually by looking at this, that there are things that are very tightly connected, but not with other things. And you can find them, and if you, maybe if the lights are good in here, you can even see that there's some substructure in here, right? So you now have a network, and now we can start looking for substructures in that network. But at the base, the network is just fluctuations in the bold signal and Pearson correlations between them. Now, I want to claim that this model was not invented to explain anything, is not intended to explain anything, is not used to explain anything. The nodes are not working parts of the brain. They might just be 3 millimeter cubes arbitrarily chopped into the brain. And the edges are not causal relationship, but correlations in this low frequency bold signal that lasts somewhere between 10 and 100, where each cycle lasts between 10 and 100 seconds. So it's not the kind of thing that we think of as part of how we engage in various cognitive tasks. And nobody thinks that this matrix explains how brains work. But everyone thinks that it represents topological structure. So what is this used for if it's not used to explain things? And notice that this reflects the point that I was trying to make earlier. Here's a network, but it's not an explanatory network. And why is it not an explanatory network? Because it doesn't describe the right kind of stuff to be an explanatory network. So what is it used for if it's not doing explanatory work? Well, the first thing that it's used to do is to discover large-scale organization in cortical organization. So again, we're going to use this method where we're going to look for nodes that are more intensely connected with one another, functionally connected, that is, intensely correlated with one another, than they are with other things, with other nodes in the system. And the way that we do that, the algorithm that we use, basically takes a very complicated network where the tips of my fingers are nodes and the fingers themselves are edges. And we're going to place a fictitious robot, a bot, at one of those nodes. And then we're going to send it on what we call a random walk. And a random walk means that it moves in a random direction to a node that it's connected to. And then we're going to see how frequently it gets trapped in certain portions of the network. So as it's on its random walk, if it's over here, it's likely to keep bouncing around between these guys. Then eventually it will pop out and pop over here, but then it will start moving around between these nodes and get trapped there. And by keeping track of how long the bot gets caught in different nodes of the network, we can find clusters that are more strongly connected with one another than they are with things outside of that network. So this is an algorithm for detecting this kind of modular structure that I introduced earlier. Right? But again, it's modular structure in a functionally connected network that is a correlational network. Okay? So we use the clustering algorithms on this data to try to pull out these subcomponents that are more tightly connected with one another than they are to other things. And what falls out of both the aerial analysis and the voxel-wise analysis is a set of brain regions that are not spatially contiguous with one another. Here, these are color-coded, right? So here's some yellow, and here's some yellow. All of those areas are fluctuating with one another in resting state bold. And we put them together because of the tight correlations in their fluctuations. But again, that doesn't mean anything of it. It doesn't tell us that, in fact, they are connected to one another by a single synapse or even multiple synapses. It just says that they're fluctuating with one another. And the thought is that we can mine that data using these tools to reveal areas of the brain that seem to be bound together in some way. So one use is to merely get these kinds of brain maps, these sorts of organizations in the brain. Some of them are familiar. Here's visual cortex. And you would expect lots of visual cortex to be connected with visual cortex. But this thing, the default mode network, no one had heard of that until we started doing resting state functional connectivity. It didn't even show up until we started looking at these correlational maps. And there are others. Here's somatosensory and motor cortex. And you can see that the colors go across them and seem to divide rather into hand and mouth, areas and mouth areas, rather than, well, you get the idea. So not only does it replicate areas that we expect to find, but it also tells us some interesting things about the organization of the brain that are at least suggestive hypotheses that we might probe further. Another thing that we can do from this is to try to find ways to carve, it's a novel tool for carving the brain into working units. I think a fundamental problem for any science is to decide the basic parts that it's dealing with. And when you're dealing with the brain, for any of you who've actually looked at a human brain, it doesn't wear its organization on its sleeve. It looks like a homogeneous mass to some extent. And you're probably familiar with Santiago Ramon y Cajal, who did these sorts of Golgi stains. But then there's also Corbini and Brodmann, who used the laminar organization of the cortex to find where one area of the brain stops and another one begins. So it was simply on the basis of the distribution of cells in the cortex that you tell where one area begins and ends. And we've been using this map since Corbini and Brodmann invented it. What I'm going to tell you now is another way of doing something very similar to what Corbini and Brodmann did. And this is a paper that Tim Laumann was working on. Suppose you want to know where the edge, where the boundary is between two different brain areas. Well, if you've got these correlational networks, you could start with a seed area here and get its correlational profile. That is, how is it functionally connected to everything else in the brain? And now just move it gradually, looking at the correlational profile at each of these points in between. And the thought is that at some point you're going to see an abrupt shift in the correlational profile of this brain area. And where you find the correlational profile shifting, that's an indication that you've moved from one brain region to the next. So where Corbini and Brodmann used the distribution of cells as an indicator of when you've moved from one brain region to the next, these guys are using correlational networks to find when you've moved from one area of the brain to another area of the brain. Here's the project that I was assigned. It failed. I was assigned, I was really happy that it failed. I was given 160 brains, 80 of which were male and 80 of which were female, and I was told to go find the differences between men and women in the brains, or to see if there were any. And I thought, oh man, this is exactly why I got into philosophy of neuroscience, was to get rid of this kind of project. But anyhow, it was, why not? So we did. And this is a comparison between the correlation map that we got from men and the correlation map that we got from women. And I think you'll see that it's empty. That is, no, and there are a couple of little isolated dots, but those don't mean anything. Just trust me on that. No difference whatsoever. But the idea is that if we had an idea that there were different types of human beings, maybe people with schizophrenia and people without schizophrenia, or people with depression and people without depression, or people with Alzheimer's disease, people without Alzheimer's disease. Maybe we could find in this data a distinction between those two types of people. And maybe that distinction would reveal something about what's different in their brains that's responsible for the behavioral differences between those two groups. And in fact, this is the kind of thing that people are increasingly doing. For autism or for Alzheimer's disease, trying to find places where the brains of somebody with Alzheimer's disease differ significantly in their correlation networks from those that don't have Alzheimer's disease. And the idea here is that it might be of some diagnostic value. Not explanatory value. Maybe it tells you something interesting about where something's going wrong, but the network by itself doesn't tell you that at all. It tells you where to look. The last bit that I'll tell you about that I think is really interesting that came out of this work, and it's, this paper is now out, it came out in 2015. In classical neuropsychology, the gold standard is a pure case of a person who has damage to one and only one area of their brain. And you want that because you want to study what they lose when they lose just one area of the brain. When you get, but neuropsychology is hard in part because brains don't break in ways that conform to that requirement. And it's very rare that you find somebody that really has damage to just that area of the brain. And what I want to suggest is that this method really gives you a new way to think about the data itself, where very messy data might be interesting. So the people that I worked with noted, this is a map of the United States, and here's a portion of the United States that includes 4 sub-regions, 4 states of the United States. This area includes those. This one's in Texas. Right? It's all in Texas. And the intuition here was that areas of the brain that have this kind of organization, that is areas that contain parts of many different networks within them, are places that if you damaged those would produce widespread deficits out of proportion to the size of the lesion. Whereas if you did damage to areas of the brain that were relatively functionally homogeneous, Texas, for example, that you would get very small deficits relative to the size of the lesion. So they took people who had damage to an area like this, where there are many different systems represented in that area, and people who had damage to an area like this, where there's just one system thought to be in that area, and then they sent to clinicians a request. Tell us how disabled you would expect this patient to be based on the location of this lesion and the size of the lesion. And what they got back was a complete underestimate. Even very tiny lesions to this area produced global deficits across many different cognitive abilities. Whereas even large lesions to areas that were functionally homogeneous or structurally homogeneous produced relatively small lesions. part of what I think is interesting here is that now you've got a case of patients that have very messy deficits, very messy cognitive consequences of their lesion, but they're evidentially very interesting. The way that they used to simply be data that you couldn't do anything with. Now we have some way of making sense of what's going on in those cases. All right. So the point that I'm making for the last 15 minutes is that these networks, because they're made out of correlations, they're not made out of the right kind of stuff to do explanatory work. What they're used to do, they're not intended to do that either. Instead, they're intended to be used as a kind of discovery tool, a tool for learning about the structural organization of the brain. It reveals possible causal variables that we're interested in, and those might be, in fact, explanatory. But the network model itself isn't intended to explain anything. These tools give us a way of taming the complexity of the brain, but they do it by aiding us in discovery, not by providing explanatory models. So remember the questions that we started with. Are network models explanatory? I think that depends on what they describe. It's a content-neutral bit of mathematics. Are they explanatory in a manner that's distinct from mechanistic explanation? Well, maybe, but not just because they're network models. Network models can be used to describe mechanisms or not. We currently have no theory of mathematical explanation for natural phenomena that blocks the asymmetries of the flagpole in the shadow, and so until I have an account of explanation of that sort, I'll hold out, I'll be an agnostic on this question. Are mathematical and topological explanations of natural phenomena free of causal assumptions? No, that's the point of Hempel's curse. And finally, so what are they good for? Identifying parts and discovering systems and describing the complexity and the organization of those systems. Now, I don't know if this is news to the scientists that are involved. When I showed this paper to the people who trained me on this, they said, yeah, that's right. And in a sense, I thought I was just reporting back to them what they had already said. But the one thing that they would want to insist upon is this last bit, that the work that they're doing with resting state functional connectivity provides a really novel window on the organization of the brain. But the network models that they use to get that window are not themselves representations of mechanisms or mechanistic explanations more generally. And so I'll just stop there.
We can think about for trying to understand it. So I wonder if is it really possible to get rid of that that trend of trying to find mechanistic explanations. From the beginning, from the 1776, when they started like this paradigm of trying to understand the brain based on understanding the parts of this logical subtraction. So I mean, it seems to me that there's attention between trying to be mechanistic when you're trying to understand the brain, and at the same time seems that it is not possible.
Yeah, I think part of the reason why people are eager to see network analysis and mental models as revolutionary in the Kuhnian sense of bringing with them novel norms of explanation. Part of part of where that idea comes from is the sense that we've been trying for 150 years to understand how brains work, and we're frustrated haven't made more progress, and we still can't cure Parkinson's. Well, we can. We still can't cure all of the disorders that we want to cure, and so maybe the explanation for that is that we're approaching it with the wrong tools and the wrong idea of what an explanation is, and that we have to shift fundamentally what we think an explanation is in order to get what we want. I'm of the opinion that science, and science including neuroscience, is very hard. And that 150 years is simply not enough time to let that research program bear its fruit. In fact, in many areas of neuroscience, we do understand mechanisms. We understand the mechanisms of action potentials. For C. elegans, we can trace out to the synapse exactly how various systems work.
In epilepsia, I can tell you how habituation and sensitization work in epilepsia by tracing the connections between the cells. And so I think those give us some sense that the mechanistic
approach to these things is not fundamentally misguided. And furthermore, for me, the idea, I have an engineering soul in some ways, that the proof of scientific theory is ultimately in how useful it is to do the things that we want to do. And what do we want to do with neuroscience? We want to cure diseases. We want to prevent diseases. We want to restore movement to limbs that are paralyzed. Fundamentally, the reason that we invest the kind of energy that we do in the neurosciences, the kind of money that we invest in the neurosciences, is because we have some conviction that at the end of that long arc, we will have some sense of how we can intervene to change the brain and make it work the way that we want it to. And the notion of mechanism that I'm working with is just that. It's that the goal of science is fundamentally to find the buttons and levers inside. The goal of neuroscience is fundamentally to find the buttons and levers inside the brain that we could possibly use for the purposes of achieving the ends that we have in terms of curing patients and eliminating devastating diseases. And so long as that remains our goal, understanding the causal structure of the system is absolutely essential. I think it goes too far to suggest, therefore, that these tools are a move away from what is fundamentally a mechanistic approach to understanding how brains operate. They're rather tools for dealing with the complex mechanisms that we find here. And what I want to do in this talk is not to somehow suggest that network analysis is not special or that it's uninteresting. I really hope that in the last 20 minutes I've made the case that I think it's very exciting and has lots of new resources for representing the mechanisms in the brain. But part of the point of that simple flagpole in the shadow example is that those networks will only give us the buttons and levers in the brain if they put their finger on the causal structure. And that is to say, if they put their finger on the mechanism. And so networks are representational tools. And so I think it just mislocates the revolution. The revolution is not in our understanding of explanation. The revolution is in the tools that we can use to discover those mechanistic explanations. And that's the case that I'm trying to make today. And why do I care? If people start just building network models and assuming that they've explained something because they've got a network model, that strikes me as moving away from the goal that we've got. If people just build dynamical models of things, but those dynamical models don't tell us how to intervene on the system and make it change and make it work the way that we want it to, then it's moving us away from the goal that we have, not towards the goal that we have. And so my insistence on the importance of mechanism and causation to our understanding of explanation is not merely a retrograde insistence that we approach this system the way that we always have for 150 years. It's rather grounded in a political conviction about what we want out of this science and how we should orient ourselves towards this science if we're going to make it do the things that we want it to do. So yeah.
Thank you very much for your talk. I agree in a general sense with what you said here, and I also agree with the idea that networks are not an explanatory, network models are not explanatory, but the goal would be that we can extract some explanation of what we are searching for with this kind of models, right? So you say that this kind of question would not be a good question. Then my first question will be, which would be a good question for this kind of stuff? And the other comment that I would like to do, and it's not a question because it might put you in a trouble, but taking into account your answer to Paola, you said that the base of these kind of models, or the goal of these models are based in the idea that they want to cure some kind of diseases, right? Is it right? So my
The
question,
value of causal models.
yes. So my question there would be the goal of people who is financing this research is to cure disease or is to prevent diseases, because this would be a very subtle difference, but I think that a really important one if we really want to make these network models explanatory for those kind of questions. I don't know if I was clear, but
Yeah, you were very clear. Your first question, it's true that I think it's bad. I do not intend to say that network models are not explanatory. What I intend to say is that some are and some are not. And the way to distinguish the ones that are from the ones that are not is by looking at what they represent. And whether they represent the right kinds of things to count as explanatory. So that's fundamentally what I think about that. What is a good question about all of this is, I do think that one problem in contemporary philosophy of science is that we find some interesting science, and then we have to make it philosophically interesting somehow. And then we go to the cupboard, and we open up the cupboard, and we say, what are the interesting topics in philosophy of science? Explanation, confirmation, discovery. And then we pick out one of those, and then we try to jam the science into that container that we pulled out of the cupboard. And I think that the issue here is not explanation. What's really interesting in network science is not so much explanation, but representation of complexity. That's one thing that I think is an interesting feature. The way that it aids discovery. And one question that I think is really particularly interesting in this work, that algorithm that I described for determining when you've got clusters. There are 40 different algorithms that one might use to do that job. And they all do it differently. And they don't agree on the clusters that they generate. And now the science is operating based on a decision that they're going to use one of these clustering algorithms rather than the other. And I think there's a really interesting philosophical question that I have not yet engaged, and may not have the skills to engage, frankly, of which, what would tell us that we're relying on these algorithms to tell us what the brain parts are. So how do we know that we're using the right clustering algorithm? And what makes a clustering algorithm the right clustering algorithm? And I think there are answers to that question. For instance, you might want to run it on test cases. So we have all this data about the dolphins communicating with one another, and then this dolphin dies, and these pods go off with one another. So take the data about dolphin communication prior to the death of that dolphin, run your clustering algorithm on it, and see if it generates these two groups. So you've got a test case where you think you already know what the modular structure of the thing is, and now you run your algorithms and see whether it tells you what you already knew. That would be one way to test it. But then there are all these assumptions that are built into all of these clustering algorithms. And if we're going to increasingly automate our discovery processes and rely on these kinds of hidden algorithms for telling us what the fundamental units of our science are, that the question of what those algorithms are, how they ought, what they ought to be, what's good and bad about different algorithms, that strikes me as very, very interesting. Because I think that this business about clustering is a way of getting at ontology. It tells us what are the subparts of our world. And these clustering algorithms are tools that help us to answer that question. So for me, there's something really philosophically interesting about the idea that we now have a mathematics that might automate our ontology. And then the question of how do you decide which mathematics is appropriate for that ontology becomes especially pressing. So there's an example of the kind of thing that I think would be much more interesting than the question, is this an explanation or is it not an explanation? But I think philosophers often will take this interesting science and try to put it into the explanation bucket, rather than digging into the science and finding what's really, really exciting there. And at the end here, I was trying to say, it's really not about explanation, it's about discovery, and here's how the tools help us with discovery. And discovery, to me, is another perfectly good philosophical topic.
Sorry. Thank you very much. Okay, maybe you're right, and maybe network models are not for explanation. But what about the other task of science, that is to predict? You think that network models predict? Do they predict in successful ways, or not really, or prediction and causal prediction and explanation are very, very linked to each other, that you cannot have prediction without explanation?
Yeah. Before I answer that question, can I answer your second question? This will be very quick. I just forgot about you. Your second question. Yes, I care just as much about curing diseases as preventing them, and just as much about preventing as curing. And I think both of those things require an understanding of the causal structure of development and the causal structure of the brain. So I think that when I say control and cure, I also mean prevent. And so thank you for correcting me on that. Now, on the issue of prediction, I do think network models can be used to make predictions. The dolphin case is an interesting one. If this one dolphin is highly central in the communication networks in this pod, and it disappears, then you do predict that you'll get two distinct groups. And I think that this thing that I showed at the end, this beautiful work that Jonathan Powers did on the network organization of the brain and the Texas versus the Four Corners case, there's a prediction that nobody would have made before network analysis. The concept of high modular density, which is at the heart of that prediction, an area that contains many distinct modules within that area. That construct didn't even exist prior to this network work. And it made predictions about the severity of the deficit that no classical clinician would make based on the size and the location of the deficit. So now, by understanding this network structure, it does allow us to make novel predictions about how the thing will break and how the thing will work. But I would emphasize that the main point that people take from the flagpole and the shadow example is that prediction and explanation are not the same thing. But I do think that there's predictive value in these models. Yeah.
Can you? I hope I can formulate this question properly, but you mentioned, you distinguished your proposal from the representationalist view, according to which the value of the, I don't know if the value of the model, I guess, or the explanation.
The explanatory power.
The explanatory power of the model relies on its representational capacity. But then when you account for what differentiates network models that are explanatory versus non-explanatory, you refer to the fact that they represent the causal structure. So it looks like, on the one hand, you're washing your hands with respect to representation, to say it in some way, and on the other, representation does play some sort of role in the evaluation of models. And I wish I could hear you say a little bit more about what the relationship is between representation and the evaluation.
Great, thanks. It was crucial to the development of physics that calculus came along. With calculus, we were able to describe things that we couldn't describe before, and model systems that we couldn't possibly model before. And algebra, similarly, was an important invention for the development of some. The Cartesian plane was a crucial development, a representational development that allowed us to conceptualize the world in new ways. And I think that network analysis is a form of mathematics that brings with it new conceptual schemes that allow us to break the world up in novel ways and show us something really quite interesting about the way that the world is organized. And so in that sense, I think that the representational tool brings with it conceptual resources that allow us to see things that we could not see before. And in that sense, network analysis is a very important contribution to our understanding of neuroscience. The only point that I wanted to make is that we can't judge whether it's an explanation or not by simply answering the question, is it a network model? You have to ask the further question, what is the network model being used to represent? If it's representing band membership, well, I mean, it depends on what we're trying to explain, but you know, co-citation networks or these correlational networks, or they're not used for the purposes of giving explanations. They're used for other purposes. So the limited point that I want to make is not. I'm a huge fan of network analysis, and I think that it is a significant advance in our ability to deal with the immense complexity of the biological and social world. But whether a network model is explanatory turns not on the fact that it's a network model, but on what that model describes. Bill Bechtel, in the past year or so, has taken to claiming he's an idealist. I can't believe this about Bill. I mean, he certainly knows what idealism means, and he cannot be an idealist in this sense, because it is important to him that our models represent mechanisms. And if they represent something that's not mechanistic, then I think he's got to back away from the idea that it's explanatory. And that's the point that I'm trying to insist on here is really just that. Does that address the worry that you had? Now, please, go ahead.
I guess my question was a little bit more general with respect to the mechanistic account that you articulate based on the ontic view. So we are going to evaluate. The idea is to address the issue of if a model is explanatory or not with reference to the ontic mechanism. But then, I guess there is a representation. So we are representing that ontic mechanism in one way or the other. And so you have to cash out those mechanisms that do not represent the causal structure, the actual ontic structure. So it seems that the way we represent does have value on the mechanistic account. It's just not very clear to me if it's not going to be a representation is good. I mean, basically what I see is that it has a representationalist tone to it, even though, and so I wanted you to spell out what that representationalist tone would be, but more in general.
Yeah, so I think we use the word explanation in many different ways. Sometimes we use the word explanation to talk about a communicative act. I explain something to you. And I think, so that's one way. And sometimes we talk about explanations in terms of representations. And there's nothing wrong with that way of talking, and I think there's obviously something right about that you know, your neuroscience textbook contains, as it were, explanations for action potentials and neurotransmitter release and the like. And I don't mean to rule that out or to suggest that it's not important to develop novel ways of representing things. But there's also this other way of talking, the way that we talk when we say that human fossil fuel emissions explain global warming.
or that Hurricane Matthew explains the destruction in Haiti. When we say those things, we're using the word explains in a different sense. And I've tried to put emphasis on that second one. But in putting emphasis on, in demanding the necessity of that second way of thinking, or that second way of talking, I don't mean to reject the importance, obviously the way that scientists construct and convey and communicate explanations, always in the form of models. My concern is with what distinguishes the good explanations from the bad explanations. And my point is that you can't answer that question by directing your attention only to the model. You've got to look out of the model and see what the model represents. So I really do want, I think you put it really nicely, that I need both of these things in a way. There is a representation of this thing, but the constraint, but our understanding of what this thing would have to get right in order to, what this representation would have to describe correctly in order to properly count as an explanation rather than a predictive model, rather than a useless model, that you can't leave out this ontic component. And so I don't mean to, because so many people are on the representational side of this, it can sound like I'm attempting to reject everything that they're after, but that's not correct. I'm merely trying to insist that what they're doing cannot be the whole story, and cannot even be at the heart of the normative story that we want to tell in philosophy about how to distinguish the good from the bad explanations. Yeah.
Hello.
Hello.
I have two questions. If in the network analysis it's not a tool explanation, maybe all is possible. But I think this is not convenient because of the time and the resources, and this is not enough. Why are the limits of the concept and network analysis? And on the other hand, what is the part of the element of causality in the network analysis?
Sorry, what was the?
What is the part of the causality, or I don't know, it's like
Part of causality.
In the network analysis.
So, I mentioned Sebastian Sung's book, I Am My Connectome. And he says, I'll map out every cell and every synapse in the human brain. And when I have that, I have you. And that cannot be right. Surely the structural connectivity of the brain is an important constraint on how the brain behaves. But it's not the only constraint on how the brain behaves. Synapses can be active or quiescent. They can be turned up or turned down. So merely knowing that there's a synapse there doesn't tell you what happens at that synapse. Need not even tell you whether it's an excitatory or an inhibitory synapse. Need not tell you what kinds of neurotransmitters are involved. So there's a case where you've got you could have a complete structural connectome of C. elegans, for example, but still not understand how it works. And so I think there are limits to structural models. Causality doesn't play a role in structural models, and it doesn't play a direct role in functional connectivity models. But many people, like Yuri Alon, I showed you one of Yuri Alon's networks, he's explicitly interested only in causal network models. And people like Clark Gleamore, who build causal Bayes nets, the people in machine learning who work with causal Bayes nets, those are people who want to build models of specifically causal networks, where the edges represent causal relationships. Now, as for the limits of network analysis, I think I'm better talking about the limits of specific implementation. Structural connectivity will only take you so far without effective connectivity. Functional connectivity will only take you so far without effective connectivity. I can talk about that.
as for I think the limits of network analysis, I don't have any a priori thoughts about where it will, what its blindnesses are, what its biases are, where it leaves, where it cannot provide answers that we want. I think it's a really good and interesting question, but I don't have an answer for it. So.
Okay, we can continue now.
I understand that there are network analyses that explain and there are network analyses that do not explain. And the ones that do not explain are, one of the things that are lacking is an understanding of the causal structure of the phenomenon. And I know that causality is a very difficult topic in philosophy, but since, for example, sometimes causality is understood as a mere correlation between things, how are you thinking about causality in order to avoid these things?
Yeah, thank you. That's a great question. I didn't say anything about what causality is in this talk. I simply helped myself to the notion. And then I said, oh, these are merely correlations, not causation, so not explanatory. So I think it's a very good question. What's different, there are many correlations in the world, but only some of those correlations remain in place when you intervene to change the value of the variable. Barometers are predictive of storms. And that's because there's a tight correlation between the falling of the needle in a barometer and the appearance of a storm. But if I break the barometer, or I open its face and push the needle down, I can't make a storm happen. And so for me, and this goes back to this engineering idea, the idea that what I really want fundamentally is a way of thinking about explanation that's closely tied to the human need to control the way these systems behave or the way that they develop. And so for me, a causal relationship is often indicated by a correlation, but that the correlation remains when you intervene on the variable and remains stable, and so that you can, I don't know why I'm saying this in such a complicated way. X causes Y if I can wiggle Y by wiggling X. And that's what I mean. With some qualifications.
We can thank you again very much.